Alright, welcome back. Math 1720, Chapter 8, Section 6. We are done with the book after this section here, so end of the semester. Things are going well. Alright, we're going to end here with parametric equations, graphs, and applications. I'm not sure how many of you guys have actually messed with parametric equations before, okay? But we're going to come up with some basic rectangular equivalents. We're going to do a cycloid, but let's go ahead and dive right in. So what is a parametric equation? Okay, it's a plane curve, and we're going to use a set of points, and we're going to be graphing two equations at the same time, but we're going to be graphing them as functions of time. So I know that you've done, like y equals x, squared plus 5, and then on line 2, y equals x squared plus 10, or something like that, graphing two equations at the same time. This is a little bit differently. We're graphing two functions at the same time to create a plane curve, I should say. So x is going to be a function of time, and y is going to be a different function of time, and we define them over the same interval. Okay, so when we start seeing these as parametric equations, we're going to see an x equals f of t, a y equals g of t, and our parameter in both of those. Okay, notice that x and y are no longer the variables in the equation, because we have an x equals equation and we have a y equals equation. Well, the only way to do that in your calculator is to be in parametric mode when we do this, and they're both as a function of time. Okay, so we want to be able to graph this, okay, parametrically. So we have the function x equals t squared, and we have the function y equals 2t plus 3. We're going to graph it for t on the closed interval, -3 to 3. And we're going to graph all the sets of the order pairs for x and y when we do this. So we're going to be substituting in values for time, and we're going to be getting out ordered pairs in terms of x and in terms of y. Okay, so we can make a table of corresponding values. Alright, so we're going to start with what? T is going to go from -3 all the way to +3. So we're going to plug t into the x equation, and we're going to plug t into the y equation, and get the outputs for x and y based on those inputs of time. Okay, so that should be pretty basic for us. Simple substitution. So when t is -3, -3 squared is +9. Okay, and then we put -3 into the y equation. You have -3 times 2, which is -6, plus 3, which is -3. Okay, so we substitute in each t value, and remember that brackets is the interval. So you're going to plug in -3, -2, -1, 0, 1, 2, and 3 for t, and you're going to get back all the corresponding x and y values as you substitute them into each individual equation. Okay, so when we substitute those in, we get this graph. Okay, so this is a parametric graph. So x and y are both functions of time. Alright, so we can see how everything is created here, and we can see as we trace the curve the direction of t, okay, as t increases or decreases what we're getting here. So the direction of the curve traces as t increases. Alright, so we can see what's going on through the curve. Alright, so we can also put this in your calculator. Alright, and you have to set up your steps when you do this. Alright, so the first thing you need to do to be able to enter this into your calculator is you have to hit mode. Okay, and you need to go down into parametric mode. I'm on a TI-84 plus, but you can see where it says function, PAR, POL, and SEQ. If I go over next to function, I hit PAR and I make sure PAR is highlighted. Okay, now when I hit y equals, notice that I now have x1 sub t or y1 sub t. So I can now graph in parametric mode. Okay, so to put in the two equations, the first equation you got to put in is t squared. So if you hit the button on your calculator below mode, see how it has x, t, theta, and n? Those are for different graphing techniques. So if you hit the button right below mode, you're going to hit that, and it's going to say t for you. Don't hit alpha t, it's a different t. Okay, and then squared. And then go down to the next line. Okay, and you're going to put in the second equation there that was 2t plus 3. So you're going to hit 2t plus 3. Okay, and then You can hit graph or zoom to see how you want it to fit. I tend to hit zoom 0 just to see what the graph looks like. But that doesn't always put it on the screen, because if you hit zoom 0, you're only going to get like half of that parabola. Okay, so what you need to do is on the screen here, there's predefined windows that you can change your graph to. So if you hit window, alright, and you type in your t minimum is -3, your t maximum is 3, put what your t step is in, so 0.05, okay, then you're going to put your x min in to be -2, your x max will be 10, okay, put your y min is -4, keep going down the screen, the other stuff's on the top right hand of the screen, so your y max, or I'm sorry, your step there, okay, your y max is -4, so I got sidetracked there, and then your your y min is -4, your y max is 10. Now when you plug all those in and you hit graph, alright, you should be able to go to your the graph that's on the screen here. Alright, and you should get the top half of the parabola and you should get the bottom half of the parabola now. So just double check that when you hit window, you have all these settings in for t min, t max, t step, x min, x max, x scale, y min, y max, and y scale. So just verify that. So once you put those into the window and then you hit graph, don't hit zoom or anything like that, change your window, then hit graph, you should be able to get this parametric equation in here. Okay, also when you hit second window, you can change the table setup and look at those sort of things, or if you hit second graph, you can look and it has the table for the parametric equations in there, so you can see what happens if, when you plug in the values of t and what you get back out for x of t and y of t. Alright, so parametric equations, we're graphing two separate equations to get x and y points based on a function of time. Okay, so let's do another one here. We want to find a rectangular equation for the plane curve of x1. Okay, so we have x squared, y equals 2t plus 3, and t is -3 to 3. This is the same example as example 1. We're going to do something different though. We're going to find the equation for this function now. Okay, so all we did before was graph the function in example 1. Now we're going to actually find the rectangular equation for this curve. Okay, so we have to eliminate the parameter of t. So we're going to solve either equation for t, alright, and then substitute it into the other equation. So this is very important. So pick the easy one. Okay, so we know that y equals 2t plus 3. That's a unique solution, right? Because there's only one value there that t is going to end up being. Whereas if we chose x equals t squared, when we square root that, we get plus or minus, so we have two different possible solutions. So that's why it's easy. Choose the easier one, which is 2t plus 3. Alright, so when we solve that for t, we get t equals y minus 3 divided by 2. Okay, so we've solved the first equation for t. Now we're going to substitute it into the second equation. Okay, so we're going to replace t squared with the quantity of y minus 3 over 2 squared. And we're going to simplify that out. So you should square the numerator and the denominator. Squaring the denominator gets us 4. Squaring the numerator, remember, it's y minus 3 times y minus 3, so you need to FOIL all of that out. Okay, but we don't necessarily need to do that because what are we looking for? We're looking for an equation. That just means something in terms of y equals x type scenario. Okay, so we can rewrite this as, we're going to multiply both sides of the equation by 4. So we're going to get 4x equals y minus 3 quantity squared. Okay, so there's our equation. Alright, so because t is in the closed interval -3 to 3, x we already know from the previous example is from 0 to 9, and y is from -3 to 9. Okay, we did that in the previous example looking at the tables. That happens if we plug in, if you plug in -3, right, into t squared, you're going to get 9, okay, and then if you plug in that entire interval there, okay, so you're going to get 9 for the x, and you're going to get the -3 for the y, if you guys recall doing that from example 1. Okay, so The rectangular equation for this is 4x equals y minus 3 squared, and our interval, okay, for x is 0 to 9. Okay, then we can define what the interval is for y. Okay, so what we need to do next is we're going to graph the plane here. This is example 3. So that was example 1. All we did was take those two equations and we came up with a single rectangular equation for those. Okay, an equation in terms of x and y that's related by t. Alright, so this is the next example here, example 3. We're going to graph the plane curve defined by x equals 2 sine t, y equals 3 cosine t. Alright, for t is from 0 to that little question mark should be 2 pi. So you can still do this same thing in parametric mode in your calculator, but you need to make sure that you change the calculator mode from degrees to radians. Make sure you're in radians and you're still in parametric mode. If you leave it in degrees, it's going to screw this up. So make sure that you're going to do that in radians mode. Okay. A way to simplify this for us, okay, is we can use the fact that we know that the Pythagorean identity is sine squared t plus cosine squared t is equal to 1. So we can rewrite these a little bit, okay, and that's where these are going to come from. So we know that if we apply this piece here, and we have to solve later on, we're going to use that. So when we do that, we can apply, alright, squaring both sides of each equation. Okay, this is going to help simplify. So we're going to square x and square 2 sine t, and we're going to square y and square 3 cosine t. This is going to help us relate everything into one equation here. Okay, so we have x squared is 4 sine squared t, and then we have y squared is 9 cosine squared t. We just did that by doing both sides. Alright, that way we can do some substitution now. Alright, so if we solve for sine squared t, we get x squared over 4. If we solve for cosine squared t, we get y squared over 9. So this is a good technique for us now that we can actually write the circular piece for this, okay? So we're going to substitute back into the Pythagorean identity here because we know that sine squared plus cosine squared equals 1. So we can actually write this as x squared over 4 plus y squared over 9 is equal to sine squared t plus cosine squared t, right? And then we replace sine squared t with plus cosine squared t is equal to 1. So our final equation here is x squared divided by 4 plus y squared divided by 9 is equal to 1. So there's how we can do that. Okay, so there's simplifying it and putting it into a curve situation. Alright, so before, there's two parts to this problem. Okay, the first part, you're going to graph it in your calculator and analyze what it looks like. Okay, not really going to go over that one too much. But then this part, this is finding the actual equation for this function, the curve. Now, let's think about this. Before, when you were asked to graph something, you know, you were asked to graph a circle in algebra. You got x squared over 4 plus y squared over 9. And you have to graph it. It's actually like an ellipse, right? Because the radiuses are different. So you were asked to graph that, but you had to graph two different versions, right? You had to graph the plus and you had to graph like the minus to get the entire piece. Well, that's the whole reason we have parametric equations, okay? If we graph them parametrically, so this one, if we graph x equals 2 sine of t and y equals 3 cosine of t, you don't have to do two separate graphs on rectangular. It graphs the complete curve for you. Alright, so that's why we use parametric equations to complete the graphs for those. Okay, so this is technically ellipse, right? And how do we know that? Well, if the denominator was the same on both of those, it would be a circle, right? Because the radius would be the same all the way around. But we have a different radius, okay? So the radius is 2 in the x direction and it's 3 in the y direction. Okay, so that's how we know that this is an ellipse when we graph this. Okay, it's based on the denominator of the function here. So when you graphed this in your calculator, right, though, you were able to graph this piece here. So what's cool is really analyzing this. You can graph this now visually. Look at the x equation. It's 2 sine of t. Well, think about that. 2 is the radius of the ellipse in the x direction. Look at the next equation. It's 3 cosine of t. 3 is the radius of the ellipse in the y direction. Okay, so you can almost, graphically looking at this, or just looking at the equation and understand what the graph is going to look like. Okay, especially, all right, so if we have, two functions that are sine and cosine, we're going to complete a circle essentially. And it's really interesting how from algebra, right, you have the equation at the bottom that's x squared over 4 plus y squared over 9 equals 1, but it really stems from the trigonometry, the parametric equation that's above, that's x equals 2 sine t, y equals 3 cosine t. All right, and you can play around with your steps and your maxes and mins and things like that when you graph this, but you should be able to graph this in your calculator, and it'll graph a complete circle. All right, so very good tool for us using parametric equations. Okay, so parametric representations of a curve, they're not unique, and there's many parametric equations or representations of different curves. Okay, all right, so now we have to go the other direction. Okay, so before we had two parametric equations, okay, and then we were able to find the rectangular version of them. Now I'm giving you, the rectangular version, and we have to find the parametric equation. So we need to find like an x equals a function of t and a y equals function of t for us to be able to do this. Okay, so we have to kind of choose what's a good choice for t. All right, sometimes, let's guess and check with this scenario, but for us, the simplest choice for us to do this is determine what you want x to be. All right, so for us, the simplest choice is, let's say x is equal to t when we do this equation. So we can change all the x's with t's. It's a good choice because it's almost a direct substitution. All right, so as long as we say x equals t here, our y equation now becomes t minus 2 quantity squared plus 1. Okay, so we could have chosen t to be something else. We could have said, all right, t is t plus, or I'm sorry, x is t plus 2. Okay, then if we had to put that into the y equation, that would have given us t plus 2 minus 2 quantity squared, so our y would have given us t squared plus 1. Okay, sometimes we can do it with trig functions. We can say that x equals tangent of t plus 2, y equals secant squared of t for all of t. Okay, so that's what we would have gotten there, right? Because we would have put in tangent of t plus 2 minus 2 quantity squared. All right, and when we squared that, we would have got tangent squared plus 1. That tangent squared plus 1 became our secant squared plus t. So these are just alternate forms, okay, that we can do. So, it kind of fits what are you looking for and what are your needs. So there was 3 different ways we could have done this. Okay, next we're going to do a cycloid. All right, so the curve traced out by, I'm just going to read the definition here. The curve traced out by a point at a given distance from the center of the circle as the circle rolls along a straight line is called a cycloid. All right, so what are we doing? We're tracing out as it moves around the circle. Very, very important function here in calculus. Okay, and how we define a cycloid is as such. A cycloid is defined as x equals a of t minus a sine of t, and y equals a minus a cosine of t, for t from negative infinity to positive infinity. All right, so we want to graph the cycloid here. We have x of t minus sine of t, y equals 1 minus cosine of t, for all of t on the interval from 0 to 2 pi when we do this. So make sure that your calculator is in radians. So go ahead and put it in your calculator, all right, in parametric mode and in radian mode. All right, you're going to look at your table. Okay, you can come up with a table of values. You guys should know how to plug all these in. All right, but the important part is taking a look at the graph. Cycloid that we use for time travel, not like back in time, but time of travel, because the shortest distance between 2 points is a straight line, but the fastest time between 2 points is a curve, and that's where we actually invoke a cycloid type scenario. Okay, but histochrome is a very good example of that as well. It's a different type of graph. All right, so we can plot the ordered pairs. okay, from the table. And you know the little bubble thing that you have that's in your calculator, it's kind of the little cycloid piece as it goes through the curve when you graph that. All right, when you change how it displays on the graph. All right, but if we plotted the order pairs, we would get this graph right here shown on the right hand side. Okay, so what's going to happen here, right? That P, that's as the circle rotates around and goes through the cycloid graph. So what is a cycloid, right? It's a flexible quarter wire that goes through the points P and Q. So that's really what we're talking about. So if we take this cycloid, all right, and we allow this bead to go through this cycloid, okay, due to the friction of force gravity, it's going to accelerate faster. Okay, and this is what I was just talking about before. Why do we use cycloids? Because it's the shortest time, okay, is this curve in a cycloid. Shortest distance between 2 points is a straight line. Shortest time is a curve. Okay, so it's very important. That's the concept we're trying to get out of here. So if we use the cycloid here that you see between P and Q, and we were able to, you know, drop a bead that goes through a string, okay, it would be the same kind of thing. It would be much faster, right, if we created that curve for it to loop up to the other side versus if it was a straight line. All right, so let's do an example so that it kind of makes sense to you. If a ball is thrown with a velocity of v feet per second at an angle theta with a horizontal position, its flight can be modeled by the parametric equations given here. All right, x equals v cosine of theta t, all right, and y equals v sine theta t minus 16t squared plus h. Okay, we got two variables going on now in each scenario here, right? We got height, okay, and time, and we got theta, and we got velocity. So we got all these different variables that are coming into play here, okay? So time is always in seconds, height, the initial height above the ground, okay, and theta is the angle that it's thrown at or released. So if you were to graph this, notice that we have what? V cosine theta, V sine theta. That's the vertical, sine is the vertical component of that, and cosine is the horizontal component of velocity. So the velocity has, we're still a vector, right? We have a horizontal component and a vertical component, okay? So that's how we would do this equation right here, okay? So if we have a different one, okay, we have 3 golf balls that are hit simultaneously into the air here at 132 feet per second at angles of 30, 50, and 70, all right? So we're going to assume the ground is level to determine graphically which ball travels the greatest distance here, okay? So we got to know what are those different things. Well, those are our thetas. Our 30, 50, and 70 are our thetas, okay? And we know that 132 feet per second, that's our velocity. Okay, so for this example, let's assume the ball is at ground level. All right, it's a golf ball. Yes, we put it up on a tee sometimes, but let's assume that it's not, that it's just sitting on the grass right now because we're somewhere on the fairway or close to a sand pit or something like that, right? So we can't put it on a tee. All right, so we want to find which one's going to go the greatest distance. All right, so we have 3 sets of parametric equations here. All of them are going to use h equals 0, and we're going to substitute in those 3 different thetas here using the same velocity for each one. Okay, so when we substitute in these 3 equations, all right, so you're able to put these in your calculator. Okay, so you have your x1, y1, x2, y2, x3, y3. And we're doing this right with h equals 0 here. So you're able to find the horizontal component and the vertical component for each one of these. Alright, so if you graph the 3 sets on your calculator, which you guys are all able to do, let me know if you have troubles getting this graph, but you got to play a little bit with some things. Alright, so look, the x min that you have on here is 0, the x max is 600, the y min is 0, the y max is 400. So make sure that you're using those with that part of your window in your calculator so that you can get the graph looking the same way that we have here. Okay, so we can look at the 3. Which one, you know, travels the greatest distance? Obviously it's the middle curve, right? Or x2 and y2. I think that was 50 degrees as we're looking at, right? So max is going to happen obviously at 45 degrees. You know, we throw it up too high, it's going to lob up, all right, or we shoot it too low, it's not going to get high enough to get far enough trajectory, things like that. So just a, an example of, this is how, if you're a golfer or something like that, they use these kind of techniques to help correct your swing, because they can kind of predict. Same if you go play like a virtual golf game, and they calculate, how far you hit and those sort of things. Slight adjustments in your ankle, okay, or your wrist. All right, so we can use the trace feature on your calculator. So that's just the trace button that's next to the graph button, and you can find and travel through that, or you can look at the table, but you can trace. All right, and as you go trace along the second curve there, you can see that the ball travels 540 feet roughly on the middle curve, okay? Which ball reaches the greatest height? Well, we can step back and look at the graph. We already know which one's going to reach the greatest height. Let's figure out why, though. Okay, so we have x3, y3. So that third parametric equation, that was 70 degrees. Okay, well, it was obviously hit with the greatest angle as well. So we're going to estimate the height on this one when that happens. Okay, so taking a look at this, right, we're looking at x3, y3, or that third parametric equation that was hit at 70 degrees. So we can use the trace feature there on the calculator and be on that curve, and we can see that roughly at 70 degrees it hits 240. You can also go through your table, guys, and see the same things as well. So scan through your table. Just change your table set so you don't have to go by one, since you're going in. You don't want to go 1 foot at a time. Maybe change the steps in your table to 10s or 20s or things like that. That'll really help you. But just use your calculator as your tool for this section. Makes life pretty easy. So we can see the highest this ball gets is about 240 feet in the air. All right, let's do another example here. All right, Jack launches a small rocket from a table that's approximately 3.36 feet above the ground. All right, now we have an H. Okay, we're going back to those first couple equations. Now we have an H. Its initial velocity is 64 feet per second. Okay. And it's launched at an angle of 30 degrees. So now good, we got everything. We got velocity, we got height, we have the angle. Okay, we want to find the rectangular equation that models this path. Okay, now what type of path does the rocket follow? So a couple different questions here. All right, but we have everything we need to plug into our parametric equations. Okay, so we go back to the base ones. We're going to use x equals, or 64 cosine of 30t. That's nothing new. We're just substituting in our velocity and our angle in there. And then we have y equals 64 sine of 30t minus 16t squared plus, this is new, right, because we have an h here, 3.36. So we're just substituting into those parametric equations from before, okay, for the cycloid stuff. Okay, and we're going to do some calculations now. Remember, what did we have to do before, though? We had to solve for one variable in terms of another and then stick it into the other equation. So we had to do that. We've already done an example like this, just not with something that included velocity and an angle and things like that. Okay, so what we can really do is we find the value of cosine of 30, we find the value of sine of 30. You guys should know that. We've done that all semester long here. All right, so it's square root of 3 over 2 for cosine of 30, right? So we multiply that by 64, and we end up with 32 square root of 3t. And then the other one simplifies down, right, into negative 16t squared plus 32t plus 3.36. All right, once we substitute inside. You can plug it in your calculator too and get decimals. Just make sure that your calculator is in degrees mode when you guys do this. Okay, so now that we know x and y, we can easily substitute in. We got to solve one of those for t. Obviously, it's easier to solve the x equation for t. All right, and substitute that in for t into the y equation. Okay, so we solve the first equation, and t is x divided by 32 square roots of 3. Don't necessarily rationalize the denominator yet, all right, until we substitute it in, because when we're going to square one of those and it'll actually clean that up a little bit. All right, so we substitute each t into the other parametric equation. So we have y equals negative 16 times x divided by 32 square roots of 3, all quantity squared, plus 32 times our t here, which is x divided by 32 square roots of 3, plus 3.36. That was our height for our equation. All right, so when we simplify all this down, You can plug it into your calculator or do some rationalizing. We end up getting this equation here. Okay, y equals negative 1 divided by 192x squared plus square root of 3 over 3x plus 3.36. Alright, so this equation defines a parabola. So remember the second part of the question is, what kind of path does it take? It takes a parabolic path because it's a parabola. Okay? Alright, we're going to carry on to this. One more example here. So we're going to determine the total flight time and the horizontal distance traveled by the rocket that we just did in the last example. Okay, so we're going to stick with the same equation here. We want to find, how long it was in the air and how far it traveled. So we have our equation here. That's going to tell us the vertical position of the rocket at time t. Okay, so you analyze this. So what we have to do, and this is just going back to basic algebra, we have to determine when it hits the ground. Okay, so we're going to solve it for when its vertical or its height is 0. You guys did all of this in algebra. So we're going to set 0 equal to negative 16t squared plus 32t plus 3.36. Definitely not something very easy to solve, or as far as factoring and doing those things. Just use the quadratic formula, alright, and that'll give you what you're looking for. Alright, so remember that that's negative b over 2a plus or minus the square root of b squared minus 4ac all over 2a. We've used that multiple times this year, so you guys should have that memorized, or at least be able to access it quickly. Alright, once we solve the quadratic formula, we're able to determine two different solutions out of this. Okay, the first solution is negative 0.1, the other is 2.1. Obviously, negative 0.1 doesn't make sense because we don't have negative time when we've launched a rocket. All right, we cannot go back in time. So the only viable answer for us to choose from this is 2.1 for t. Okay, so 2.1 tells us what? When it hits the ground, right? We're assuming we launched the rocket at time equals 0. It launches and it comes back down. When it comes back down, that's at time 2.1. This is literally just an algebra problem here. So now we know how long it's in the air, all right, and based on that, we're able to calculate, how long or how far it traveled. So we're going to take that t equals 2.1, and we're going to substitute it into our parametric equation that relates to our horizontal component. The horizontal component is the x. Okay, so we're going back to the parametric now. We know how long it was in the air, and we're going to take that time because we're using the horizontal component and we're substituting t, and so we know the total distance that it traveled in the x direction, the total horizontal amount of distance. Okay, so we're going to substitute in 2.1 here into our parametric equation. So we got approximately 116.4 feet. That's how far it traveled. Okay, so we got to step back and kind of revisit this problem here. So just to reiterate what we did, okay, we used our parametric equations, all right, in example 7, and we were able to solve for t, and we took t and we substituted it into the y equation for the x, all right, and we came up with our equation that was our parabola in terms of time, okay, and then we were able to find, using the quadratic formula, how long it was in the air, and then we took that time and substituted it back into our original parametric equation for our horizontal distance to see that the rocket traveled 116.4 feet. Okay, you might have to watch these ones a couple of times as you're doing the assignments. I know they can get a little tricky, but also if we put this in the calculator, okay, you can also use the trace command for this as well. So if you put the equation in and we put the parametric equation in, if you traced this all the way out to the end, you'd approximately get 116.39. So calculator, really good tool for you guys in this section of this chapter. But guys, that's it for parametrics, all right, for what we have. If you have any questions, feel free to email me or ask me any questions in class and we can go over some more examples. All right, guys. Have a great day. We'll see you in class.